So free energy and equilibrium. That standard free energy change, delta G, determines the spontaneity of reactions. K, the equilibrium constant, is going to determine how far a reaction goes towards the products. The larger K is, the more negative the standard delta G will be, and the products will be favored. If K is smaller, then delta G is going to be positive, and the reactants will be favored. I did it to myself again. Derive the relationship between K and delta G0. Okay, so we had this delta G for the reaction was equal to delta G0 for the reaction plus RT natural log of Q. Yes? At equilibrium, what does Q equal? K. At equilibrium, Q is equal to K. What can we say about delta G at equilibrium? At equilibrium, does the reaction go forward or backwards? No, it doesn't go forward or backwards. Delta G is 0 at equilibrium, right? It's not spontaneous in either direction. So we can take those things and plug them into this equation. Delta G is 0. Plus RT natural log of K. I can't remember which way they do it. We could see that delta G is equal to negative RT natural log of K. Or we could say that RT natural log of K is equal to negative delta G, which, those are really the same thing. The equilibrium constant is related to the standard free energy change. If you think about this math too long, you'll be like, how does that even work out so simply? So we won't think about it. Here we have different things going on. So here we have A to B where K is less than 1. So K is less than 1, so the extent of the reaction is going to favor the reactants, right? Here is the standard condition where pure A and pure B, they're both gases. They have to be equal at 1 atmosphere. So this one is going to have a positive delta G. This one, where K is larger than 1, the standard conditions fall right here, and so that forward reaction is going to be spontaneous. Delta G is negative. And here, at equilibrium, Q is equal to 1. And delta G would be 0. Again, I forgot to put the animation. Well, at least we know what we're shooting for. Calculate delta G, the standard free energy change at 298 K for this reaction. So we need to use that equation that we just came up with. So the ideal gas constant is constant. The temperature here, I'm throwing us a bone and just giving it to us in Kelvin. And then we're going to do the natural log of K, and K is going to be 81.9. Delta G is negative, telling us that this reaction under standard condition is spontaneous in the forward direction. Kp is bigger than 1, which tells us that the products are favored, and so both of those things match up. Any questions? So we just saw how the free energy change depends on the equilibrium constant. And we've also seen how the free energy change depends on temperature. And we know from doing experiments that the equilibrium constant is also changing with temperature. So we can combine those two equations and make a linear form, and that ends up being this guy. So the natural log of K is equal to negative delta H over R times 1 over T plus delta S over R. So Y equals mx plus b. So this is our Y, and this is our x. So if you graph the natural log of the equilibrium constant versus 1 over the temperature in Kelvin, you'll get a straight line. The slope of that line is going to be negative delta H over R, and the intercept will be delta S over R. Now, of course, there's a qualification here. It's useful over a limited temperature range, so you can't, go to crazy high or crazy low temperatures. But what this means is by measuring the equilibrium constant at different temperatures, we can make a graph and we can calculate the standard enthalpy for the reaction and the standard entropy change for the reaction. So we can make that into a 2-point form where you don't actually have to do the graph. So here, now we can't find the standard entropy change because we've lost the intercept, but we can find delta H by measuring the equilibrium constants at 2 different temperatures. Or we can find an equilibrium constant at a different temperature if we know what delta H is.